Okay. So this is a conversation using the jargon of hypothesis testing. And as we go along, be sure to ask questions. I'll try to keep my eye over here. If you want to ask questions with the private chat, the recording will include a transcript of the public chat, but if you chat privately to me, that does not go in the transcript. And so if you want to ask questions, you know, you can either just jump in and say something. Keep your mic muted, except, you know, when you want to jump in, but feel free to jump in. Or do a public or a private chat. You can raise your hand in the participants window, but I'll check every now and then, but I may not notice that for a few minutes. Okay, so here we go. So this engineer says, I think I can make a better light bulb, a better method. And of course, the manager wants to know, so how's it better? All right. So the engineer says a lot of things. He says, our current bulbs last an average of 1,000 hours with a standard deviation of 100 hours, and their lifetimes are normally distributed. So he has a very complete model for the distribution of lifetimes of the bulbs currently. But he thinks, the engineer says, I think with my new method, the average lifetime will be around 1,050 hours with a standard deviation of 80 hours. Ooh, you got an extra 50 hours out of it. And they're more predictable, the standard deviation smaller. So this engineer is pleased. Well, if you were the manager, what would you want to know? Anybody, just jump in there. What would you be wondering about after this discussion?
Maybe how many he's tested, how many new light bulbs he's produced.
Well, there you go. I mean, what evidence does he have that this is a real phenomenon? Yeah. So, you know, the manager says if that's true, we should consider changing our process. How much will it cost to make the change? The engineer says about $1 million. Well, so the manager then needs some strong evidence that the new bulbs are lasting longer. What evidence does the engineer have right now? The engineer says, I made 9 bulbs and burned them out. And the sample mean was 1,050 hours, and the sample standard deviation was 80 hours. So now, still thinking like the manager, what are you worried about now? Is there still anything to worry about?
But the sample size is too small.
Yeah, you look at 9 bulbs, I am not convinced, you know? Okay. So, as Christina said, well, maybe the engineer just got lucky. The 9 bulbs are just a sample. It could be that the population mean is still 1,000 hours. The new method didn't really do anything. Okay. So what would, let's get somebody who has not yet answered. What would make you, the manager, feel more confident that the bulbs really last longer, the new bulbs really last longer than the old ones? Any new person? No? Jump in there. Let's see. Well, Connor, what do you think? Still there? Oh, I know what we can do. 10?
You call me?
Yeah.
Because I'm doing a test, that's why.
Okay. So we're trying to figure out, let's do this by the private chat because no one wants to speak. Okay. So throw some stuff into the chat for the manager's worried that this sample of 9 bulbs, just lucky, and really maybe the mean is still 1,000. So what would you want the engineer to do?
So I guess like the engineer have to work in hard to get.
Do some more work.
Yeah, right, more work.
What kind of work?
So like you mentioned, like because the engineer, right?
Yeah. Like here's what the manager is concerned about, right?
Yeah.
The 9 bulbs were just a sample. So what could you do to make the evidence more convincing?
So I guess like because the manager want to get more confident, like to get 1,000, right? So that's what like the engineer have to like more work to get.
Get a bigger sample.
Yeah. Because I mean a large sample.
Yeah.
Uh-huh.
Somebody else just came in on the private chat, said, get a larger sample. Okay. And would it not also be nice, besides getting a bigger sample, to get some kind of calculations about the probability? Don't we want to know what's, the probability of a type 1 error or a type 2 error? We need the alpha and the beta. The engineer's worried about the type 1 error. I mean, the manager's worried about the type 1 error. Okay. So, oh, I don't know why these are disappearing. Hang on, this is problematic. I'm sorry. Okay. Hang on. Okay. Okay, so a bigger sample would help, and some probability calculations would help. Now, how confident would you need to be before you would consider spending the extra money? Okay, so 99% is a reasonable kind of, wow, they just disappear. Okay, I just got to do it in this mode. I'm sorry, yeah, the fly-ins, they fly in and then they just disappear. I don't know. So anyway, you could ask for 99% confidence because the engineer will be able to achieve it. It sounds like you want him to be really sure that his bulbs are better. But all he has to do is get a big sample. And, so we'll do a calculation of how big his sample size has to be. But it's not going to have to be that huge. and he can get 99% confidence. So the manager is going to demand this to be the confidence level. Okay. So now we can formulate the whole thing as a hypothesis testing problem. So the null hypothesis here belongs to the manager. X is normal, mu is 1,000 hours, sigma is 100 hours. The alternative hypothesis is that the population mean is bigger than that. And the factual evidence that we have so far is that a sample of size 9 came up with 1,050. The common mistake here is people will see that 1,050 over here under the factual evidence, and they will think that that is the alternative hypothesis. But it's not. It's about the sample. The X bar 9 is about the sample. It's not about the population. So it's not a hypothesis, it's a fact. Okay. And your alternative hypothesis, the engineer has no chance of proving that the population mean is exactly any particular value. Because when every time he gets a different sample, he's going to get a slightly different sample mean. You really, you can't prove that mu exactly equals any particular number. So that's why the whole thing is always formulated as a specific null hypothesis versus a broad and general alternative hypothesis, like just mu is greater. And then the burden of proof is just to show that under the null hypothesis, whatever your evidence was that popped up was just unlikely. Okay. So now the manager's worried that this sample mean over here with the tiny little sample was just luck. So what the manager wants to know is, what's the probability that you just got lucky? Now what the manager wants to know is, what's the probability that your sample mean would be 1,050 or more if mu was really 1,000? Got that? The probability. He wants to know, what's the probability that out of all the different samples of size 9 that you could get, there's a million ways you could pick your 9 bulbs. He wants to know, out of all the ways you could pick your 9 bulbs, what percentage of them would give a sample mean this big as 1,050 if really the population mean was only 1,000. Does anybody know the name for that probability? Just put it in the chat. You can do the private or the public chat. The name for the probability of getting such an extreme value of the sample mean. Wow, okay, I got 3 answers. They're all wrong. Okay, yeah. So this is, make sure you get what I'm saying though. The probability that your sample mean would be so far out if the null hypothesis was true. Now we got it. That's the p-value. That's the p-value. Now somebody said alpha. Alpha is closely related, but it's not the p-value. What alpha is what's the probability, it's how small would the p-value have to be before you consider it strong evidence against the null hypothesis. The p-value is how far out is my data. The alpha is how far out does it need to be. I think the pictures and the slides for the rejection criteria PowerPoint set that up. in a way, you could review that there. Okay. So now on to the next slide. So what evidence should you calculate to assess, or what should you calculate to assess the strength of the evidence? The p-value assesses the strength of the evidence. Low p-value means strong evidence against the null hypothesis. Low p-value means you saw something that you should not see, that would have a low probability under the null hypothesis. Anybody want to like jump in with a question on that either?
So was the answer to your previous question the p-value, or?
Yeah, I think I was looking at this slide and I was just saying, you know, what is it we have to calculate to determine how strong is this evidence?
Got it. Okay.
Okay. And another way to say how strong is this evidence is to say, what's the probability that you just got lucky?
Oh, probability. Okay, that makes sense.
If that probability is really low, that's strong evidence. You say there's a 1 in a million chance you would just get this lucky under the null hypothesis, but it's what happened, you know? So then either the null hypothesis is wrong or this 1 in a million event just happened. Right? That's evident. That makes you think the null hypothesis is wrong. Yeah. If you could say,
Right.
yeah, if you could say, what's the probability I just got lucky? 1 in a million. Oh, I didn't get that lucky, so the null hypothesis must be wrong. Okay. So low p-value, a p-value below alpha means reject the null hypothesis. P-value, how far out are we? Alpha, how far out do we need to be? And when I say far out, I'm talking about like what's the area in that little tail out beyond. Okay. So back to the conversation. Manager says, maybe you got lucky, your 9 bulbs is just a sample. Maybe the population mean is still 1,000 hours. What's the probability that 9 bulbs from the population would just happen to have a sample mean bigger than 1,050 hours? So the engineer does a calculation here, works out the area to the right of 1,050 under the blue null hypothesis. Let's go through this a little bit. Why is it 1 minus?
Because it's greater than. You're looking at the right side.
Yeah, because we need, why are we looking at the right side? It's jumping back to an earlier slide. See, it's this alternative. We're only going to be convinced if our sample mean is real big. And we need what's the probability we got that big just by chance. So it's all about what's the probability of being bigger than 1050. So since it's bigger, you got to do the 1 minus. Norm dist will give you the area to the left of 1050, but we want the area to the right. So it's a 1 minus. Don't always just do 1 minus. You got to look at the alternative hypothesis so you know which side. Are we doing an area to the right or to the left? And so, but that's how you decide. Then the other question comes up every now and then is, well, so why is the square root of 9 down there?
The sample size is 9.
Yeah, it's the sample size, and it's because we don't care about what's the distribution of x. It's the distribution of x bar. We want what's the probability that the sample mean is bigger than something? The sample mean, the X bar has a standard deviation from statement 2 of the central limit theorem. The standard deviation of X bar is this part that I've selected here that's got the square root on the bottom. And so we get an answer. The p-value is about 6.7%. So the engineer, the manager looks at that and says, wait a minute, you want me to spend $1 million, and there's almost a 7% probability that you just got lucky with this tiny little sample. Under the null hypothesis, there's a 7% probability that you just got lucky with the sample. So the engineer says, well, if you're wanting to be 99% confident, then our significance level, alpha, is 1%, and you want me to do a hypothesis test at that level. And the manager says, yeah, that's what you need to do. Okay. So now the engineer's got to go out and do this test. What does he have to decide? He's got to make a bunch of bulbs and burn them out, right?
You need to find the sample size.
Yeah, he's got to decide how many bulbs, how many bulbs do we need to make?
Oh my, 30.
Hey, Jonah.
I forgot the exact number. More than 30 or 32.
Oh, okay. Now there's something to understand here. The low 30s thing, 30 or 32, somewhere in there, that just would matter if your variable x was not normally distributed. See, in order to use our hypothesis testing methods at all, to even get started,
Yeah.
you need a simple random sample that's representative of the population of 1.
Yeah.
And 2, you need just either, not both, just either
Oh, yeah.
x is normal or the sample is big. Now in this story, it was part of the null hypothesis that x was normal.
Oh, really? Oh, yeah.
So we don't actually need a big sample for that reason.
Yeah.
And that's why when we did the p-value calculation, it was already okay to use norm.
Okay.
Yeah. If we had not known sigma, we would have used t, but it would have been okay either way.
Okay.
But now this thing we're worried about now, it's not that we need, the sample's already big enough to make the method valid. But why does the engineer possibly, why do we want a bigger sample? Because we want to reduce the probabilities of errors. See, the engineer failed to achieve the 99% confidence when he only used 9 bulbs. Okay. So the engineer is thinking that probably a type 2 error happened. He failed to reject the null hypothesis, even though he still thinks the null hypothesis is wrong. in the engineer's mind. So the engineer's thinking a type 2 error happened, and he wants a bigger sample to drive down the probability of a type 2 error. When he goes to figure out how large is the sample, in this story, it's not because he's worried about validity of the method. It's because he wants to make the error, the type 2 error probability to be smaller so that he can convince the manager. Talk to me about that. Is it anything on that? Looking over here at the chat. Don't see anything in the chat. Okay.
I'm sorry, I think I missed the question. What was it?
Oh. So my question was just after we decide, okay, the manager's demanding 99% confidence, and so the engineers got a task to go out and get a sample, and if he's going to reject the null hypothesis, he has to achieve this 99% confidence. And my question was, so what does the engineer have to decide now to get started? And the student said he's got to choose the sample size. And then another student said, maybe that's the 30 or 32, low 30s idea. And then I launched off into this big discussion of, well, glad you're thinking about the 30 and 32 business, but in this story, it's not relevant because we know our null hypothesis says X is normal.
Isn't there a formula for
Sample
calculating?
size, yeah. So when we got our formula for the margin of error, the E, you say E equals, and it's got something with a sample size in there. So you can solve that for N. And so we had a homework problem where you had to find N in order to achieve a specific margin of error. So here's the formula. It says, well, if you want to get your margin of error down to a certain size, here's the sample size you need to do it. Okay, now I know we're doing a hypothesis test. We're not making a confidence interval, but we can still use this formula to help us figure out how big should the sample be. And the idea here is we want a big enough sample that we can be pretty confident that our sample mean is not going to be very far away from the truth. How far away? You see the conversation. We can figure out how far away, how much error can we tolerate, plug in a number for the E, then we can work out what sample size will be big enough to achieve that using this formula right here. So the engineer says, okay, the manager wants alpha to be 0.01. The statistician says, okay, so you can figure out the Z star, the critical value for making a two-sided confidence interval. With alpha equal 0.01, you can work out the Z star. Okay. And so the thinking is, even though we're doing a one-sided hypothesis test, if we make our sample big enough so that a two-sided confidence interval is a little short interval, so that whichever hypothesis is right, whether it's the 1,000 or what if it's the 1,050, okay, either way, we want a sample big enough that we can make a little confidence interval around our sample mean that's going to rule out one or the other of those two hypotheses. We don't want to get a situation where they're both, you know, inside the confidence interval and they could either one of them be true. You with me? You're going to get a sample, you're going to get a little sample mean, put an interval plus or minus around whatever you get from your sample, put this little interval up there. You want it to be a short interval so that it's either going to have the manager's 1,000 in there, or else it'll have the engineer's 1,050 or something like that in there, but not both. Okay. And so we'll go back to this formula. We'll plug in the Z star for 99% confidence. We'll plug in the sigma, okay, which is either, well, the manager thinks it's 100 and it's always been 100. Maybe it's 80 according to the engineer's recent data, but you know, just make a big sample. So use the 100, right? Use 100 or an 80 either way, but a big sample is always good. So you can throw in the 100. And this way, and then, so we'll have the Z star from the 0.99 and we'll have the sigma, you can use 100. And then all we have to do is to figure out what do you want for the E in order to separate the two possibilities. Okay. So here's our Z star. And I'll do another slide with another picture to figure out what about the E. But here's the Z star, you know, we're working at 99% confidence. You got half of alpha out on each end of the distribution. And 99% in the middle, 0.5% on each end. And so the Z star here, it's the edge of the lower 99.5. 99% in the middle and the 0.5% on the left end. So the total area to the left of the Z star is 0.995. And so that's how you get the Z star. And it came out to be 2.576 STDs. Okay. Now about the E. Oh yeah, now one more comment before the E. That was the Z star for all this work I'm doing with trying to figure out the sample size. It's not the Z star that we'll use when we get around to doing our hypothesis test. That's a one-sided test. For that one, the Z star is going to be 2.326. So you're with me? It's two different things. It's the 2.576 for the two-sided confidence interval. But when I get around to doing a one-sided hypothesis test, it's going to be the 2.326. It's two different numbers.
You can do the two-sided with the one side because you're looking at like an area, like taking on it, like the confidence interval is like an amount of area. I don't get why we can use two.
Why it's two different problems. When we do the hypothesis test, we're going to reject the null hypothesis if the sample mean comes down far out to the right-hand side. if the sample mean is anywhere over here in this top 1%, that's when we will reject the null hypothesis. So if your sample mean, which is to say your z-score, the sample mean in hours or the z-score in STDs, same thing, just standardized, right? If your sample mean comes down more than 2.326 STDs above the mean, that is when we will reject the null hypothesis. So this one, the 2.326, that will be relevant to our hypothesis test. But before I even get there, I have to make some light bulbs and burn them out, and I have to know how many to make. Am I thinking about how many bulbs do I need? I'm thinking about that this way. I'm saying, once I got my sample mean, I want that to pin down, where's the true mean, to within plus or minus some distance. Plus or minus some distance. Two-sided plus or minus. So that's why I'm thinking about the confidence interval for choosing the sample size. Does that make sense? Okay. So for working out the sample size, I'm going to use the 2.576. I'm going to use the sigma. It was the 100. I mean, manager thinks it's 100. Engineer has a little bit of evidence it might be 80, but a big sample size is good, so just use the 100. And for E, these two people are 50 out, their estimates are 50 hours apart. So by the time you're done, you want to pin down where's the true mean to within something substantially less than 50 hours, so you can tell, which one's right. So the engineer wants, he wants to make enough bulbs that he can tell to not just within 50 hours, but substantially better than that, plus or minus, less than 50 hours. What is the true mean? So this is an arbitrary choice. It doesn't have to be exactly 25 hours, but you figure if you can pin the truth down to within plus or minus 25 hours, then we can tell for sure which person's right. Is it the 50 or is it the 1050? Does this make sense? If you wanted to go smaller, if you wanted to go 10 hours, that would be fine too. It's just got to be a lot less than the difference between the two people. So you can pin down, what is the population mean? Which one's right? You don't want the possibility that you make this confidence interval and they're both inside. Okay. So he does the calculation. He comes up with, rounding up, and gets 107 bulbs. The engineer says, look, I just want to do this once and I want to get the truth. So let's just go up a little bigger, add a few more. Let's make 120 bulbs. All he cares about is it feasible? Can I actually make that many? And he figures, okay, if I can make 120 and do the test, that's even better. And so on sample, my point here, the only reason I didn't make the slide simpler by just going with 107 was I want to make the point that a bigger sample is always better. It's better for both people, the null hypothesis and the person who believes the alternative. It's better both ways because it just reduces the probability of errors of both types. So bigger samples are always better. And now the engineer feels like, okay, 120 is going to be enough because it's my margin of error is going to be down pretty small, smaller than the difference between us. Okay. So now, so students, often want to use E equals 50 hours, but E equals 25 is better. And I want to point out why. I need to put some annotation on here. Let's see. Well, can't get my annotation tool to appear. There it is. Okay. So we don't know, that engineer's not done his experiment yet. We don't know where the sample mean is going to fall. Maybe the null hypothesis is true with 1,000, but maybe the real truth, it's something else. We don't know that it's 1,050. It's just, that's what the engineer got from the little bit of data that he has. But if it is 1,050, then the distribution curve would be this purple one here. Probably it's neither one of these numbers. Probably, not exactly 1,050. But our sample mean, regardless, our sample mean is not going to match either one of these. He's getting new bulbs. He's getting 120 of them, and the sample mean comes somewhere. So like maybe it comes, here. Maybe that's the sample mean. Make that green, it's a sample mean. Okay. Well, then the engineer is going to calculate that margin of error. And put an interval estimate around his sample mean. If he used 50, for the margin of error, you see how the data came out closer to the engineer's idea than it did to the manager's idea, but they both fit inside the confidence interval, and they could both plausibly be true. So using a margin of error of 50, is a very good chance it's not going to let you figure out, it's not going to let you reject the null hypothesis. But if you let the margin of error be something like 25, maybe I drew that a little small, then you don't have them both in there anymore. If the sample mean was closer to the 1050, the 1050 will be in there, but not the 1,000. So now the manager, the engineer thinks, okay, this is a big enough sample that if the truth is closer to my idea, it'll reject the manager's null hypothesis. So this one's big enough to have some reasonable chance of distinguishing between the two. So the statistician says, okay, you're using a 99% confidence level, so your manager is going to be happy, 1% chance of a type 1 error. And you're going to use a sample of size 120. Let's see what's going to be the probability of a type 2 error. So what if the mean is around 1,050 hours? What's the chance we'll fail to reject the null hypothesis? So now, everything from here on in is calculating beta. So this is one, we did a beta a little bit in that last PowerPoint. The first thing we have to do is find out what's the rejection criterion. Where is it over there on the left-hand edge? How long does the bulb have to last to reject with 99% confidence? Well, it'd have to be above 1,021 to do the rejection, and so below 1,021 to fail to reject. Okay. So what's the picture for that? I'm going to go back to a previous slide. See, we reject above the Z star, and we fail to reject below it. We already knew that was 2.326 STDs. We did not know, so how many hours is that? The reason we did not know is, depends on, well, how big is an STD? Sigma over square root of n. So we couldn't figure out how many hours that is until we knew the sample size. See, on either one of these curves, how wide is that curve? How much is the standard deviation? The sigma divided by the square root of n. We don't know how much is one STD till we know what n is. Well, now we've settled on n equals 120. So now we can put the 120 in there, and we know a standard deviation is 100 over root 120. And so the edge of the top 99%, that 2.326 STDs, that point, the edge of the red tip, that's 1,021 hours. To get the beta, we need what's the probability that we fail to reject if, in fact, null hypothesis is wrong and 1,050 or something close to that, we'll do what if it's 1,050 is the real mean, then what's the probability we fail to reject. So what the statistician says to the engineer, what you're asking is what's the probability that we might fail to reject the null hypothesis, even if your bulbs are better than that. And so we need to do this kind of like, what if the mu is 1,050? Then what's the area to the left of 1021? And that's easy, because norm.dist, the area to the left of 1021, we're doing it, what if the mean's 1050, like the engineer thinks? What if it's like the engineer thinks? What's the probability we fail to reject? He gets 0.004%. So now, the manager's happy. There's only a 1% chance of a type 1 error. The engineer's happy. There's only this tiny percent chance of a type 2 error. Neither one of them are very likely to get messed up. Most likely the test result will be correct. Last slide. And so the engineer made 120 bulbs, got a sample mean of 1,030 hours. Did the participants reject the null hypothesis? See, where was the cutoff? 1,021 hours. What did they really get? 1,030 hours. So that's up there in that rejection zone. See, now we know this right here is 1,021. Their sample mean came down above. They did reject the null hypothesis. So the engineer is very happy. He's quite sure, he's 99% confident that his bulbs are better. And what was the p-value after all? Go all the way back to the beginning of the story. What do you calculate to assess the strength of the evidence? The p-value. What is it? It's the probability that you would get such a big sample mean of 130 hours if the null hypothesis was true. Let's switch over to Excel. Let's just get that number. the word that's a right-tailed test. That's what makes you worried, or that's why you're doing the probability of a big sample mean. So we want the area to the right of our sample mean, to the right, so it's a 1 minus. We're using the normal distribution because we do know sigma, and it's valid because the sample is bigger than 36, and x was given to normal at the beginning. It's doubly valid. Want the area to the right of the sample mean that we got under the null hypothesis. We're answering the manager's question. If I'm right, what are the chances that you just got lucky?
Wait, are you putting in a X and a mean?
I need to put in the mean, and I just forgot to type it. Thank you very much.
Okay.
Yeah, so that's a... Okay. So there's the formula. The 1,000 and the 100 came from the null hypothesis. The 1,030 was the data. The 120 was the size of the sample. And we get this tiny number. .05%. So engineer can say, no, really, if your null, if my bulbs were just like the old ones, under your null hypothesis, you really would not expect to see such a big sample mean, but that's what happened. So that null hypothesis is probably wrong. He didn't get his 1,050. He only got 1,030, but still proved the rejected the null in favor of the alternative. Are there some slides you want to go back to, or? I'm going to end the recording now.
I have a question. I'm typing in the same thing as you.